Okay, so we're going to take a look at an important theorem in graph theory that allows us to determine by looking at a particular graph whether it's going to even have circuits or paths before we set out to try to find them. Now, in order to state this theorem, we need to begin with a definition, and we're going to define the degree of a vertex in a graph to be the number of edges attached to that vertex. So here is an example of a graph. I have here 5 vertices, v1, v2, v3, v4, v5, and a bunch of edges connected them. And I just want to find the degree of each of those vertices. So again, our definition of degree, it's just the number of edges attached to that vertex. So if I look at v1, for example, the edges attached to v1 are e1, e2, and e7. So those are the edges that again, meet v1, or basically if we were at v1, those are the edges we could take to travel to some other edge, or some other vertex. And because of that, we would say that v1 has degree 3. And what I'm going to do is just write a little 3 next to v1 to say that v1 is degree 3. Now, looking over at v2, notice that there are only 2 edges attached to v2, right? e4 and e6. So I would say that v2 has degree 2. And looking over at v3, I see e7, e6, and e5, so 3 different edges attached to that one. So v3 is degree 3. v5 has 1, 2, 3 edges attached to it, and v4 also has 1, 2, 3 edges attached to v4. So v5 and v4 are both degree 3 as well. Okay, so that's all degree means. Again, it's the number of edges attached to a particular vertex. Now, fortunately, that degree tells us whether we can find paths and circuits. So here's the big theorem, and it's going to have 2 parts to it. So first of all, a graph G has an Euler circuit if and only if each vertex has even degree. So again, we need every vertex on the graph to be an even degree vertex. So looking at the example we just did, there's a bunch of degree 3 vertices, and those are, 3 is an odd number, and therefore there is no Euler circuit. So if our task was to try to identify a circuit or a path for this graph, we would just look and say, oh, too many odd vertices, it can't be done. Now a graph G has an Euler path if and only if there are exactly 2 vertices of odd degree. And that path must begin at one odd vertex and end at the other. In one of the early examples where I was finding paths, I talked about an isolated vertex, and starting at that vertex gave me a way of finding a path. This now kind of formalizes that idea because that isolated vertex was a vertex with odd degree. Basically, if we think of an edge going to and from a vertex as a way of traveling to and then back out from that vertex, even vertices are very nice for trying to find a path or a circuit. So taking this example up here, v2 is a very easy vertex to visit because we can travel e6 and travel e4, and we are not stranded at that vertex. But v1, for example, would be a more difficult vertex to visit because we travel up to e2 and then out from e1, but that leaves e7 unvisited. So odd vertices are more difficult to form paths and circuits out of because we can take a trip to the vertex and a trip back to from the vertex, but then there's still a leftover edge. Or if it was degree 5, that's 2 trips in, out, to cover 4 of the edges, but there'd still be a leftover one that we hadn't visited. Now, again, we can create a path if there are exactly 2 odd vertices because we just begin at one of those odds and we end at the other odd, and that clears up that extra edge in each case. But other than that, we need all even vertices. Now, one thing you may notice here, we say if all of them are even, there's a circuit. If exactly 2 are odd, then there's a path. And then if there are more than 2 odds, then there's no path, no circuit. But that leaves out the case where there is 1 odd vertex. And the thing is that actually cannot happen. And the reason why is every edge connects 2 vertices. So essentially it adds 2 to the total degree of the graph. And so basically I can't just have one odd vertex, because that extra edge, that, let's say third edge, must be connected to some other vertex, which would then create that vertex being odd. That may seem a little abstract, but let's just say, I took a simple graph with 4 vertices that were all even. So something like this, where every vertex has degree 2, right? I have 2 edges attached to each vertex. Now, if I want to make one of those vertices odd, I would need to connect that vertex to some other vertex through some extra edge that I've just drawn here. But now notice I actually created 2 odd vertices, because I changed one from even to odd, and whichever one that it was connected to changed from even to odd. The only other thing to try is maybe just do a loop, connect the vertex to itself. Okay, and now it looks like there's and one odd in this case, that upper right vertex, but that loop would actually count as it would add 2 to the degree, because it's attached to the vertex in 2 different places. So even though there's only 3 distinct edges attached to this vertex, one of those edges is attached twice. So we would say the degree of this vertex is 1, 2, 3, 4. Even though there's 3 distinct edges, one of those edges is attached twice. So all this is to say that the case where we have exactly one odd vertex cannot occur. So we only have no odds, which means there's a circuit, 2 odds, which means there's only a path, or more than 2 odds, which means there is neither. And now we can finally properly address the Königsberg bridge problem. Does the Königsberg graph have an Euler path, circuit, or neither? If we look at the degree of each vertex in the Königsberg graph, vertex 1 is degree 3, because I see 1, 2, 3 edges attached. Vertex 4 is degree 3, because I see 1, 2, 3 edges attached. Vertex 3 is degree 3, because I see 1, 2, 3 edges attached. And vertex 2 is degree 5. There are 5 edges attached to V2. So what I have here are 4 different odd vertices, and since there are more than 2 odd vertices, there are no edges or circuits or paths, rather. So the question was, does it have a path, circuit, or neither? It has neither. And just to note why, it's because there are 4 odd vertices.